And both models were written in a paper, and they have been submitted, and you can find them in archive. So if you look for ALeRCE in archive, you can find like the main paper, the presentation paper, and both machine learning papers. So first I will talk about the Stump Classifier model, and then about Leica Classifier. In the first place, just about the requirements that you need to run this. Typical packages like the ones that Camilo introduced before, like NumPy, Pandas, Matplotlib, etc. And also we are using a client, the ALeRCE client for Python, but the new version, and you can install it using this instruction. So I've already installed it, and I have it there. So I'll run this cell to import the packages. And here I'll create an instance of the client. So this client will allow me to ask and to query some of the data that is contained in the ALeRCE database. So I'll run this, and yeah, I have the client. Well, before that, some of the interfaces, some of the ways that we have to access the data are the ALeRCE Explorer that you can find here in alerce.online. And that will show you a pretty interface with a filter here. So you can filter by the predicted astronomical class, number of detections, dates, etc. And then you can have the results and look at each object, see the light curve, see some metadata, classification, stamps, etc. And we also use heavily another interface called Supernova Hunter, which its main purpose is to find fresh supernova every day. So we are connected to CTF observatory, to Palomar, and every night we receive alerts, and we try using machine learning, of course, to detect which of the alerts are the most promising for supernovae candidates. And every day, a group of astronomers from the ALeRCE project check these candidates and select the ones that they think might be a supernovae. And well, the link for the Supernova Hunter is hunter.alerce.online. But first, about the Stump Classifier, here's the link for the paper that is published in the archive, led by Rodrigo Carrasco and Esteban Reyes. And the idea here is to use a convolutional neural network, a deep learning model that sees just the first image of a detection, and try to classify that image into 5 categories: active galactic nuclei, supernovae, variable stars, asteroids, and bogus alert. It's hard to classify with just one stamp into more fine-grained categories, like the tree that I think Guillermo showed before. For example, it's hard to distinguish between Cepheids and ALeRCE using one stamp, but we can do a very good job between these 5 classes because they look different in the image. So here you can have an idea of the amount of objects that we have in our training set. Is of course very unbalanced, so we don't have that many supernovae, for example, that many real supernovae to train our model. And here I will show some of the examples. I'll try to enlarge this. So as you can see, for example, here we have bogus images with saturated sources and some cosmic rays, etc., hot pixels. Asteroids. So if you look at the template image, you don't see anything. And at the science image, you see a source, and that might be an asteroid. For example, for variable stars, you might see a field with a lot of stars, and a source that is in the template and also in the new science image, but its brightness might have changed a little bit. Supernovae are in many cases located in host galaxies that you can see. So if you see a new source near a galaxy, it might be a supernovae candidate, and active galactic nuclei. In many cases, you cannot see the galaxy, but in others you can. And the model does a pretty good job detecting active galactic nuclei candidates. So the architecture of the deep learning model is shown here. Basically, we take the first detection stumps, the science image, the reference, the template, and the difference that is built using PSF matching and subtraction. And then we feed that into a parametric model that has a lot of operations and parameters that we tune during a learning process, aiming to minimize the classification error. And as you can see here, the model has will take these images and rotate them and process them with the same operations, and then join those intermediate results to further processing. It also uses some metadata, for example, the position of the object, etc. And finally, you have a prediction, a probability vector for these 5 classes. For more details, you can see our paper or ask in the chat if you have some doubts. And the cost function that we're using has 2 terms. The first one is called a cross entropy, which is very typical for convolutional neural networks and for classification in general. And the idea is to minimize the classification error. And we add a regularization, an entropy regularization that tries to avoid like over-convinced classifications. For example, if the model says with 100% confident that an object is from a given class, we have found by experience using the Supernova Hunter that that's not that useful for the astronomers to perform the manual classification. So this tends to give more spread out probabilities among the 5 classes. And this helps a little bit to astronomers to, and it keeps the good results also in the confusion matrix, and helps the astronomers to perform the classification and take a decision. So here we have the classification results over our test set. And as you can see, it does pretty well. Of course, there are some intrinsic confusion that the model cannot overcome, because if you have an asteroid that just passes over a galaxy, you might confuse it with a supernovae, for example, and there's not much you can do with just one stamp. But in general, you can do a lot. And we have shown that with many submitted and confirmed supernova candidates to the transient name server. So going to the code, the idea is to retrieve some of these results and play with them. And here I'm going to use the ALeRCE client to query some of these objects. Here I'm asking for the results of the Stump Classifier. I'm asking for a given category. For example, in this case, there's a default parameter supernovae, but I could ask for AGNs, bows, etc. A minimum probability threshold, and some other parameters. So I will run this function. And now I'm gonna ask for 2,500 objects of each class, and I'll try to get them. And this query is a little bit heavy, so it could take maybe a minute. But we're also running in Google. We have pretty good network bandwidth. So now it's ready. And as we can see in the first result, the result for the AGNs, we have many columns in this data frame. For example, we have number of detections for each object, some information about the colors, about the dates, etc., the class, and with something interesting here is that the probability given to each classification. So if you want to retrieve the light curve of a given object, we can also use the client for that. And in this case, I'm going to use the command query detections to get all the detections from an object. I'm giving here a CTF object CTF20 AAEE Lulu. And this is a really nice supernovae, and I'm gonna retrieve it. So this is the data frame. We have here the modified Julian date, some magnitudes, MagPCF, some information about the filter that we are using, the G or R filter, etc. We have many fields. And one of them is called CandID, which is an ID for each detection. So each number here defines a specific detection. And if I know the CandID and the object ID, I can go and get, for example, the stamps. So in this case, I'm going to take the brightest detection for Lulu, the one with the minimum MagPSF, and I'm going to look for its CandID. And then with the CandID and the object ID, I'm going to ask for the images. And I'm going to use the get stamps command for that. And I can take the result and unpack it, like separate it, to get the 3 images and plot it using matplotlib with the command imshow. So I will run this. And here I have it. I didn't put a lot of titles, but I can explain to you. The middle image is the template image, and you can see a host galaxy. The left one is the same galaxy, but with a bright source, which is the supernovae. And this is the difference image. And now I have a pretty large function, which will help me to do some plots for the objects. So basically I take a data frame, I do a loop for each band, for each filter, and then using some parameters of the function, for example, if it's periodic or not, if I know the period, I will fold the light curve to the plots, etc. And depending of the kind of object, I will use the original magnitude that comes from the difference image, or I can use a corrected version that takes into account the magnitude of the template and does some correction to get the proper light curve. Well, that's the most important thing. I have this command to get some object data given the object ID, and this command to run the commands before. So I'll define those functions. And now I'll go through some of the objects that I retrieved before. And I'm querying this, I'm plotting at the same time. So I'll try to go up. So for example, here I have two AGNs, or two AGN candidates given by the classifier. I could use a higher threshold, for example, for the probability if I want to get a more confident one. But the idea is that I can get the light curve and the stamps. For example, here, apparently a supernovae, but these are not supernovae, I think. But the model here might have thought that it's a supernovae because there's a galaxy, but I'm not that sure. I don't think so. It might be, I'm not sure. Some variable stars, yes?
Just a comment, it seems that is a problem with the template. Because you have the
yes, you're
the supernova at the beginning of the lecture.
Yes, that's the case. So, for example, I'm not sure, but this object might be from the beginning of the survey, for example, and the template might have been built just in the moment that the supernovae was present. So that kind of stuff can happen in CTF. So here I have some candidates for variable stars. So we have the source in the template image and the science image. Here's another variable star, and you can see there are a lot of stars there. an asteroid with just one source, which is good because here we're looking for a single position in the sky, not the complete trajectory of the asteroid. We don't have in this notebook the whole orbit or tracklet for the asteroid. So in the template, we don't see anything. And here we see a very faint source. So and there's no galaxy, so it might be an asteroid. And the same here. And some bogus objects. For example, here's a single or 2 pixels that are brighter, and that doesn't look like a PSF, so it might be a bogus object. And there are no further detections in, so it can be a bogus object. And here we see, for example, like a checkerboard pattern that might be because of a wrong PSF matching. And here it seems that there's no much difference between the template and the science image. Let's get some light curves, some information about the light curve length for the predicted objects. Basically, I'm gonna get the lengths of the light curves. I think I already have it in the data frame. I'm going to build some histograms for that using the histogram command from NumPy. And I will run this for every class. And as you can see here, we have, for example, supernovae candidates, and some of them are longer, have many detections. Some of them are very short. Perhaps they are close to the detection limit, or they might be false positives in some cases. The same for AGNs and variable stars. And you can see for, especially for asteroids and bogus candidates, that almost all of them have just one detection. That is what we expect. And for example, here we have some bogus objects in the same position with many detections, which can be, for example, sources close to saturated sources or false positives. Now I'll try to show the spatial distribution of these predictions, because we expect to find a relation between the astrophysical kind of object and the position that it has in the sky. So some helper functions to deal with ecliptic and galactic coordinates, and to transform those coordinates that I have before, to transform radix from to other coordinate systems. And then some commands to the plotting of the spatial distribution, basically taking the data frame, extracting the positions, and do the plots. I'll run this also. And finally here, just to run the commands from before. And I'll have, yes, I have 6 plots with the 5 classes and all the objects. So those are galactic coordinates, the X and Y axis. And this line is the ecliptic. And as you can see, for example, the variable stars are mostly located in the plane of the Milky Way, which is reasonable. The asteroids are mostly on the ecliptic. And we find, for example, AGNs far away from the galactic plane because it's hard to see them through the galaxy. Supernovae is mainly everywhere. Maybe there should be less here, but it's okay. And bogus objects all over the place. And we can change a little bit the previous plot and use also the confidence of the classification. So we can scale the size of the dots using the probabilities. And I'm going to do the plot right now. So this plot is very similar to the one before, but here I'm now scaling and coloring each source according to the probability given by the Stump Classifier. And for example, here in the case of AGNs, we can see clearly that the ones that are located in the galactic plane have lower confidences, and the ones far away are higher. Of course, you can find both cases in every place, like low confidence objects outside the galactic plane, for example, the harder ones. But this kind of analysis we have found, like plotting the locations of the objects, the colors of the objects predicted by your models, is very, very useful in terms of debugging the machine learning algorithms. Paula has done a lot of work in that sense. So once you train a model, you get some statistics about how it's performing over your test set, but your test set is part of the label data. And you don't know how well it's going to perform outside in the unlabeled data, in the new data, but you can do some sanity checks and, for example, check the positions of those predictions, check the colors, etc., and be sure that they make some astrophysical sense. That's an advice that we can give to you. Well, this is about basically the Stump classifier, and now I'm going to talk about the Leica classifier. I'm not reading the chat right now, but I don't know if there's any question that I should address now or maybe at the end.
There are no questions yet, but maybe
okay, so
we can give some time. But you can continue. I will let you know if there are questions.
Perfect. So at the end we can tackle any questions. So the second mode is the Leica classifier, and the idea is to use the whole Leica that we have available. And to classify into a fine-grained taxonomy, which is shown here in this tree. In this classifier, we have three main categories, like transient objects, stochastic objects, and periodic objects. Of course, there's no such clean separation in reality. For example, you can find some regularities in the pulsations of the cataclysmic variables, but this is just for machine learning purposes and with following an astrophysical inspiration that makes sense. And what are we doing? We are computing features over the light curves. We are trying to get any metadata that comes from CTF. And for example, we are also doing cross-match with WISE to get some color information, because most of the data we get from CTF is just in the G and R band. And if you can get some color information for the sources, you can do much better. Some of the features that we are calculating are an autoregressive mode, which is in the paper from Susana Ieramendi, Felipe, and others. The Mexican hot power spectrum from Arevalo et al. We are using a damped random walk from Graham et al. Some structure function.
Ignacio?
Yes?
Now we have a question by Thomas Mueller. Do other brokers have Stump and Leica classifiers as well? If so, are there any big differences? Do they use other type of classifiers?
I'm not sure. I think that there are cross-match information. I think there are other brokers that are working on developing models, mostly on simulated data or static catalogs, but I'm not sure if another broker has machine learning models running every day. Maybe you can help me out.
What I know is that Ampel has a classifier to detect early supernovae candidates.
Yes, that's right, because it appears in TNS. Yes.
Yes, and
it's not public.
Yes, not public. And Think just released a paper where they show some examples of classifications done with the CTF ALeRCE stream, but they're not done in real time. Mm-hmm. So currently we're the only broker that is applying machine learning algorithms in real time. Mm-hmm. The rest mostly apply filters, but not machine learning algorithms.
Mm-hmm. Thank you. Well, about the features, we're also computing, for example, periodograms.
Sorry, Ignacio, we have a second question.
Dale.
How the original labeling of the training dataset was done? Expert labeling, citizen science, or some older non-machine learning algorithms were used?
Yeah, that's a very good question. Most of the labeling comes from crossmatch with other catalogs that have confirmed sources. The astronomers have done a lot of work in that sense, making sure that the catalogs are reliable, because some catalogs have labels, but they are not that good. And looking for catalogs from specific classes. For example, many months ago, we didn't have a lot of labels for LPVs, although they are very, very common in our data. And other source for labeling that is very important and that has been shown to be important in these months is using expert labeling, especially for using the Supernova Hunter for the supernova early detection. So basically, every day when our astronomers check the candidates, they report some of them that are obviously bogus for them. They report them, and we annotate them in an internal catalog, and then we retrain the model to improve the classification. That's the kind of the active learning that we have done by now. It's hard in many cases to just give the light curves to the astronomers and ask them to classify them, because these are just light curves for the alerts. So all the magnitudes that are close to the template are not shown here. Those are in the data released from CTF, but no in the alerts. And also you need a lot of extra information like colors, spectral information to a classification, especially in a fine-grained way. So if you want to go to the kind of precision that requires this taxonomy tree, it's very hard to do it with crowdsourced labels, even from experts. We have tried, yeah, Dale.
We have a last question by Alex Racine. Do you check somehow for the difference of the parameter space of the train and the ground datasets? Different catalogs have different depths, etc.
Yes, we have done some experiments, for example, comparing how the label set that we have behaves compared with the unlabeled general CTF. Some of the things that we have done are taking some features, mostly the most important features, and then do some projections, for example, some visualizations, and trying to see if there's an overlap, or how good is the overlap between the label set that we have collected and the whole data set, to see, for example, if there are clusters of objects that are not well represented. We have tried some of it. And we are also working heavily on detecting outlier objects that are not in a category that we have already, or that they might not be even known in astronomy right now. But it's quite challenging, but we're working on it.
Ignacio, can I complement that
Sure.
answer? So we know that our training set is much brighter than the actual test set. So what we are doing is to avoid all the features that connect, for instance, the total magnitude of the object. So we don't bias our selection towards the brightest sources. But we know that it's hard currently to have like a training set that represents completely the test set, because we don't know exactly how is the test set. This is very new. So the approach that we are having now is to avoid features that can bias even more the selection. And we know that we are able to detect sources that are fainter than the label set in the test set. So our approach is working, but it's something that we need to further analyze, particularly for LSST. This is going to be very important because there are no previous surveys with that depth. But yes, it's a very important question.
Yeah, in terms of bias, I would say that it's very important to first be aware of it, try to think some possible bias cases that might happen in your data, try to take every measure to not take that into account in your models. For example, as Paula mentioned, removing, for example, the mean brightness or the brightness related magnitudes or brightness related features of your model, and after that checking your predictions to see if there's any bias or if the predictions are skewed with the depth or the magnitude or any other category. Well, I'll continue with the model. So we have a lot of features, and then we give them to 4 random forest models. Basically, we have 4 random forests, and the first one is in a top level, we call, and it tries to classify the sources into 3 categories: stochastic ones, periodic ones, and transient. And after that, we apply for each object, we apply 3 more classifiers that try to separate among the stochastic and periodic. And for example, in the stochastic, we have the NGNs, the blazars, etc. And basically, then we have 4 probability vectors, and then we combine it using total probabilities. And finally, we have one large vector of probabilities, and that have shown very good results in our case. So this is the confusion matrix where we show the true labels from cross-match from our label catalog and the predictions from our model. And as you can see, these boxes represent each of the 3 main categories. So for example, this kind of confusion here is expected among the different supernovae subclasses. But in general, you can see most of the classifications are in the diagonal, so we are doing a pretty good job in general. Now I will try to retrieve some of the information from the database using a different way. Instead of using the Python client, I'm going to use directly PsychoPG2. I'm using SQL queries, as Camilo showed. I'm going to take the credential, the user and password from the public repository in use cases. I'm going to run this. Yeah. So I'll do a very simple query over the probability table to show, just to show you what's the shape of it, what it contains. So these are the first 10 rows from the probability table, and this table contains a lot of object IDs. It also contains different classifier names. For example, we have here light curve classifier, which is the whole light curve classifier model. We have here light curve classifier periodic, which is this specific random forest in case you want to see that specific result, like intermediate result. And we also have all of the 4 random forests, and the Stump Classifier is also contained here in this table. And this is the class name, and this is the probability given for each classification. So this ranking means, for example, here, it means that this object was classified as an eclipsing variable by this classifier, and this is the most probable class, the class in the ranking 1. For example, for this other object, according to this classifier, is classified as a supernovae type 2 with ranking 2. So there's another category, for example, I don't know, supernovae type 1a, that is the most probable class for that object. I can also retrieve some features for an object. For example, here I'm trying to retrieve the features from the Lulu object that I showed before, and I'm showing just the first 30. So these are explained in the paper from Paula. And we have, for example, coordinates, features from the autoregressive model, periods, etc.
Ignacio?
Yes?
You have 10 minutes left.
Okay, perfect. This is a little bit heavy query. I'm going to retrieve all the classifications from the light curve classifier that are the most probable class, basically. And I'm going to get the object IDs, the class name, and the probability. So this is a simple query, but you get a lot of data, so the transfer time might be a couple seconds or minutes. Now here I have the response. I have almost 1 million rows, and for each object ID, I have the most probable class and its probability. I can do a histogram of this to see how they are distributed across our predictions. And as you can see, we have a lot of variable stars that a lot of objects that are predicted as variable stars. For example, eclipsing variables, long period variables. This category that contains a lot of different kind of periodics that we put together, which is called periodic order. And some of the smaller or the not that popular classes are the supernovae, are much rare events, and some active galactic nuclei, etc. This is plotted in logarithmic scale, by the way. Now I'm going to plot the distribution, the spatial distribution of the objects, as I did before, basically as a sanity check to be sure that our model is predicting things that make sense. In this case, I took some sources that belong to the Milky Way, long period variables, surface and stellar objects. So I'm going to select all the predictions from those classes. And now I have 264,000 rows. I'm going to get all the spatial coordinates for all the objects in our table. This query is also a little bit heavy. It might take a couple of seconds. Basically, I'm asking for all the galactic coordinates for the objects that were classified. This is almost 2 million rows. A little bit of pandas magic to put them together in a 2-column data frame. So I have 2 columns now, the galactic latitude and longitude. And now I will take 1,000 objects per class, per each of these 3 classes that I'm selecting. I'm going to do a spatial plot. So taking some objects and do a scatter plot. And in the scatter plot, I see in galactic coordinates that the objects that I expect to be galactic are in fact located pretty much in the Milky Way. And we have also some exceptions that might be misclassified objects or objects that are a little bit far away. But in general, it makes sense. And now for some extragalactic objects like QSOs, AGNs, blazars, and supernovae, I'm going to pretty much the same. First some filtering, taking some random samples, and then I'll do the plot. And as I can see, there are not so many, or there are some objects with little confidence in the Milky Way plane, and the extragalactic objects are located away from the galaxy. And now, just to finish, I'll do some visualization of the predictions of the light curves of these objects to see if that makes sense or not. So I'll take 1 object per class. I have 15 classes. So I'll do 15 plots, and I put a minimum probability threshold of 35%. I'll run this, and yeah, those are the objects that I'm going to plot. And I'm going to plot them using the command that I ran before. So this takes a little while because I'm retrieving some information, some period information. Yes, so I'll enlarge this. So basically, if there's a period candidate, I'm trying to plot them. This is an AGN candidate, a blazar candidate, a Cepheid that it's folded, but the period is not quite right. You can see that it has some structure, but it's not a clear folded light curve. So the period might be a little bit off. We have here an object with a very large error bar that maybe we should filter in post-processing if we're doing science with it. But these are the kinds of things that we find usually. An eclipsing binary candidate that might be folded with half the period because we just see one, I think one eclipse, but they might be two. An LPV that the algorithm tried to fold with almost 400 days of period. Here you can see the two light curves folded. A delta Scuti candidate that it's not well folded, but it looks like a periodic star. And other kinds of objects like another Lyre that's okay, I would say. Some supernovae candidates, superluminous supernovae, supernovae type 2, a nice supernovae 1A, supernovae type 1BC, young stellar object, etc. So that's it. That's the notebook, and now I'm taking questions.
Yes, there are a couple of questions. Let me. Oh, where is it? Okay. Have you studied the correlation between the Stump classifier and the Leica classifier?
Yes, I think Guillermo showed an image of that. It's contained also in the presentation paper. And basically, the taxonomy that we are using for both classifiers is different. So the Stump classifier has just 5 classes, and the Leica classifier has 15 classes. But they have categories that some categories that are shared between each other. So we did some sort of confusion matrix, plotting them in one axis each classifier, and we see that there is very consistent in saying that the supernovae candidates given by the Stump classifier are classified as one of the 4 supernovae categories that we have in the Leica classifier. The same for the variable stars. The variable stars from the Stump classifier are usually classified as Cepheids, Lyres, Delta Scuti, etc. For the active galactic nuclei, it happens pretty much the same. Of course, there are some errors. And the asteroids and the bogus objects usually have just one detection. So for objects that have less than 6 detections, we are not using the Leica classifier. So in general, you have very, very few sources that were predicted as asteroids or bogus objects that are classified by the Leica classifier. And those are mostly wrong classifications by the Stump classifier, but there are very, very few cases of that.
There's another question. How bad features can affect the classification with random forest? And with bad features, it means maybe 2 features are too dependent on each other.
At the moment, I think we haven't explored that much. In general, random forest is a very robust model, so you can add features, and it will make sense of them and improve your classification. The dangerous thing about that is to include things like the mean magnitude, for example, that is very biased in the sense of the labeling, and it will perform bad when you go to, for example, fainter objects if your data set is biased. But in terms of correlated features, we haven't explored that much. We know that there are some correlated features, but we haven't explored it in detail. One thing that we might try is to do some, in the future, is to do some feature selection to reduce the number of features that are computing. Because one thing that I didn't mention, but it's pretty clear from the job that we do, is that we need fast classifiers because we're doing online classification. We are receiving every night maybe 100,000 alerts or even 400,000 alerts, and for the Vera Rubin Observatory we expect to go order of magnitude higher. So the classification has to be fast, and also the feature extraction for that has to be very, very fast. So the less features that we use, or the simpler features that we use, it's better.
Ignacio, we have a complement answer to that question from Jorge.
Okay.
He said, if 2 features are correlated, random forest only select one and leaves the other one at the end of the importance ranking. Maybe Jorge wants to say something about that.
Yes, but about that, one of the good things of random forest that might happen, but each of the decision trees that we're using in the random forest sees only a subset of the available features. For example, if we have 100 features, each tree sees only maybe 10. So in some cases, one of the features might be available. In the other tree, the other one might be available. So at the end, when we have, for example, the combined probability ranking, sorry, the combined feature importance ranking, I will expect in general that both features, if they are very, very similar, to be located in the same level of importance. But in principle, that's something that you can clean a little bit in your model.
Another question that is being asked in different questions is whether we are considering to include new classes, and the answer is yes. So
yes,
for the moment we just have these 15 classes, but we are working on improving the taxonomy. And if you think there are classes that might be interesting for you, we are happy to hear your feedback.
Yeah, it would be great also if you are interested in us to include some of the classes to provide us labels. So if you have a label catalog that might have cross-match with CTF, or you have labels for CTF of a given object, that could be very helpful. You have to be careful that the object has to be variable enough to produce alerts in CTF, because we're classifying the alerts, not the data releases. And the other hard thing is if the object is very, very similar in shape and in features to another of the classes, because the classification performance won't be as good. For example, in our case, the supernovae tend to be similar between each other, at least with the information that we have, and it's tough to separate them. If we had, for example, access to some spectra from the supernovae, we could do much better, but we don't have that in the alerts.
Okay, I think with that we can finish this session. Thanks, Ignacio.
We should perhaps launch the poll.
Oh, okay.
Yes.
Yes, we had a poll. Do you? So.
Should I do it?
Dale.
Okay. So here it is.
Yeah, so we have a little poll about some libraries and some tools related with machine learning and data science. And we would like to know if you have used it before or not.
Yes, the last session is a question session. So if you have any questions, you can start writing them in the chat. If there were questions that we didn't ask and they are missing in the chat, please write them again so we can find them.
We have sent 3 answers of 89 people. Five. Well, it doesn't seem to be changing. Perhaps we can ask 96. And we have 10 more minutes for questions in general for any of the speakers.
Yes, there is one question here. I think anyone can answer this. How do you work with the periodic order label? How you select it? Maybe I can take that question. So we put all the periodic classes that are not included in the taxonomy into this box. So we have rotational variables, ellipsoidal binaries, flares. all the classes are not included. Sorry, no flares. They're not in the model currently. All the periodic classes that are not in the current version of the taxonomy goes to that label.
Okay, I think we can finish the poll. It's 79 out of 83. I will end and share. Take a picture.
So the most popular ones are scikit-learn and Topcat.
Yeah.
Yeah, just for curiosity, maybe you can mention in the chat the people that answer Keras, TensorFlow, and PyTorch. Can you please mention if you have used them, just one of them or the three of them, just to know if they are the same people or not?
I think there's no more questions.
Yeah, I'm trying to look for questions that we didn't address properly. So there's one here from Thomas Miller. Will you include other classes in the Leica classifier? For example, chart label transients like kilonovas, FPOTs, etc. Pancho, do you want to answer that?
So, sorry, what was the question? Can you repeat, sorry?
If we are planning to include chart label transients like kilonovas or fast blow optical transients?
Yes, so we were planning to do that, but of course the problem with that is that the observed label set is very small. It's just one case basically and a few candidates. So in this case, perhaps what we have to do is combine simulations and so which you can have as many as you want with a very few labels. And this is the approach we are having. But yeah, it's a very important question for SST as well. So I think for these very rare classes, you have to go that way of using simulations plus a few observations. So I think maybe Guillermo, if he's connected, can talk about using a few examples plus other data. Is he around?
Well, he's answering the chat, so. Okay.
There's a new question.
I cannot unmute myself.
Okay, I will make him a co-host. Yeah.
Go ahead.
Now you can.
Okay, thank you. So yes, we're working on this. We're working on using a small number of examples, using a model that has been previously trained with more examples, with more data. And this is in the field of transfer learning or domain adaptation. And we're doing a lot of research on that area. Was that the question, Pancho?
Yes, yeah. So it's related to.
No, the thing is, the question is, would we have something like that users of ALeRCE can just directly use? It's something that it's not in our plan right now, but we should think about it.
Okay, there's another question. I don't quite understand it, but maybe you can help me. I want to do a simple classification, and I just have 4 inputs, which are magnitudes in 4 different bands. Should I add different operations, plus, minus, multiplication, division, between them as inputs?
I can answer that. Okay. So it depends on the model. For example, if you're using a simple neural network like a multi-layer perceptron, in principle, you would expect that the model takes care of combining the features using its operations, and wouldn't be necessary in principle to use like sums or subtractions, etc. But it could help, depending on how large is your model, to include some combinations of features. So basically, it depends on the capacity of your model, like how able it is to combine the features in a clever way.
Yeah. Okay. Another question. At what stage is the development of the outlier detection algorithms? What kind of approaches are you considering? Is Manuel here to answer that?
I don't think Manuel is here, but I can answer.
Yes.
Oh, Manuel is here, so he can answer.
But he's not co-host, so maybe you should.
Maybe I can start answering, right?
Yes.
Or...
Now he's co-host.
Now
okay.
he is. Manuel, are you there? Maybe he's not here. Okay, so anyways, the thing that we've been doing is that we've been trying different methods. We have tested around, I would say, 10-ish methods, and we have tested all of them. We have chosen the best ones, and we're currently putting them in production on the pipeline. So my guess is that during the next couple of, maybe in a month or so, we'll have something in production.
Okay, we have a very nice question from Thomas Müller. In which ways can we, the community, contribute to ALeRCE? Are there ways to collaborate?
Perhaps I can comment?
Yes.
Yeah, so we are very happy to collaborate, and actually we see ALeRCE as like a national infrastructure. So we see this project in the future as kind of a critical infrastructure for astronomers to do their science. So if you have an interesting science case and you have a good training set, for example, that could help us achieve this, put this scientific case into production, please contact us. So far, we are very open to new collaborators.
Yeah, and I would add to that our job is to serve the astronomical community. So basically, one of the most important things, the thing that makes that gives our project sense is that astronomers use it. So I would say that the number one thing that you can do is use ALeRCE and use it for your science. And if you need something, ask to us. Maybe if the API commands that we are showing are have some problem, etc., you can call us, or if you need something, you can send a message to us. That's the first thing. And if you want to further collaboration or give us labels or anything, we're also open to collaborate.
Yeah, and also it will be very nice to have scientific outcomes from the astronomical community that may not necessarily involve ALeRCE people directly, but you can use our products, and that will be also very awesome, because that's the main goal of this, like we provide these classifications, and then you can work with these data sets and do your own science and publish papers. So you are more than invited to do that.
Yeah, so also adding to that, we have invested a lot of effort and time on building the infrastructure. Then there was a second phase where we invested a lot of time on machine learning, and we now need to get to the astronomical applications. So we are really, really happy to work more with scientific cases.
Okay, it's 5 p.m., so we should end this session. Do you want to say a few words?
No, just thank you everyone. Thank you the speakers, and we'll see you tomorrow at 2 p.m. And if you have more questions in between, please write to us. And I don't know, Paula, do you want to say something else?
No, just see you tomorrow.
Mm-hmm. Maybe if you want to keep playing with the notebooks or modifying the notebooks that we already showed, you're free to do it, of course, and to use it to do your own science.
Okay, thank you.
Bye.
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 Bye.